In this video, we'll be looking to see when precipitation occurs. So if your solution has enough ions or not to cause a precipitation reaction. Okay, um, so precipitation will happen. This is really goes back to an old topic, or just a general equilibrium topic, is Q versus K. So remember when I'm going to scribble out some stuff right here. So remember that, like, if you have like A plus B, okay, and then it makes like C and D, remember what Q was. So our at equilibrium, it's C times D over A times B. Or let's not even call it that. Let's just call it products and reactants. Okay, and it's products over reactants. Okay, and this is what Q equals. Okay, and let's say K was like, the equilibrium constant was like 10. Okay, so what if you had 20 products and only one reactant? Well, this our Q would be 20, okay, and it can't be 20. It's got to be 10. So if Q is greater than K, this number needs to go down, and this number needs to go up. So in order for Q to match K again, so the equilibrium is unsettled when Q is greater than K, and it needs to reduce the numerator and increase the denominator so that it could get down to 10. Okay, with precipitation reactions, of course, there is no denominator. It's just based on the product number. So when Q is greater than K, it just means you have too many ions, and the ions need to come together and make precipitate, and so that it can reduce the number of ions, so that Q can go back down to K. And it's much easier to look at this 20 and 10 than these crazy tiny numbers, but it is really as simple as that. It's 20 versus 10. And if you have something like that, then you're going to get a precipitate. So let me erase all my scribbles here. And I just pressed too hard on the slide and made it change. Okay, so let me erase all this. Okay, so technically, when Q is greater than KSP, is my notes I have up here, precipitation will occur. It's useful then to set Q equal to KSP, and then we say at any amount where Q is greater than this number, then it will cause a precipitate. Okay, so here's an example, and in this example, let me draw a picture. Okay, where we have it's saying 75 mils of 0.015 molar calcium chloride. Okay, so that means we have the chloride, is going to be a spectator. Um, and yeah, the chloride is going to be a spectator, and so is the potassium. Okay, so we don't care about those two. So we have a source of calcium ions. So we got some calcium ions in here. Okay, and it looks like we also have a source of sodium ions. Okay, so we got these guys in here too. SO42 minus, SO42 minus, SO42 minus. Now, the question is, do we have enough? So do we have enough of these ions to cause this solid to form? Okay, that's the question. So we're going to set Q equal to K, and then compare what we get for Q and compare it to this number. And if it's greater than this number, then it needs to go to the left and cause a precipitate to reduce the number of ions. So here's our precipitation reaction. So we have CaSO4. This is the solid precipitate side, and this is the dissolved side of the equilibrium. This is the dissolved, solubilized side. So is there too many ions? Is there too many ions? Or are there not enough ions, is what we're trying to answer here. Are there not enough ions? Okay, where are we? Where is Q in relation to KSP, to this number here? Okay, so let's try this. So we're going to calculate the concentration of calcium. Okay, and this is going to be the how much we had, the volume of it, times the concentration of the calcium, divided by the total volume, which was 210 milliliters. Okay, and then we get sorry, this number was 0.15, and our amount here is 5.4 times 10 to the negative third molar for calcium. Okay, and for the sulfate, we had 135 times 0.030. Okay, and over the total volume after the two are added together was 210. And so the concentration of sulfate ions is 0.019 molar. Okay, and we don't need an ice table, but it is good practice to write out the equilibrium expression so we don't forget about our exponents. Okay, in these Q versus K problems, we don't really need an ice table. We just need the equilibrium expression, the correct equilibrium expression. So 4,2 minus. So we see everything's 1 to 1 here. Okay, and so we're gonna calculate Q. So these are our initial amounts. Okay, and remember Q is done with initial amounts as opposed to the equilibrium amounts. SO4 2 minus. Okay, so this is going to be 5.4 times 10 to the negative third times 0.019 molar. Okay, and for this, I get 1 times 10 to the negative fourth. And so my KSP was 2.4 times 10 to the negative fifth. So this number, so Q is greater than KSP. So if we go back to my picture, I had too many ions. So some of these need to come together and go away. And they do that by going to this side. So my equilibrium will shift left, and it's going to make more, it's going to make some precipitate to reduce the number of ions that are swimming around there so it could get back down to K, to the K value. So this means we have too many ions. So the system needs to remove them to get back to KSP. So precipitation will occur. Precipitation will, running out of space, occur. Okay, so let's go to a slightly kind of a variation of this problem. And we're going to change around the given a little bit, or we're going to change around like what we're trying to solve for a little bit, and see if we could think this through, how to do this. So it says, the title of this slide says, what's the minimum it takes to cause a precipitate to form? So here we have a solution. Here we have a solution of sodium phosphate. And then our question, it says, what's the minimum concentration of silver nitrate that would cause precipitation of the solid silver phosphate? So in this problem, we already have some phosphate ions. So we got some PO4 3 minus. And we don't have any silver yet. We're going to sprinkle some in. Okay, so here's a little salt shaker. Okay, and we're going to sprinkle in some Ag ions. Okay, how much, so our question is, how much Ag will it take to create a precipitate, to create Ag3PO4? Okay, so how much of this do I need to add? Okay, by way of, and not it's asking for molarity. or sorry, the problem's asking for molarity, and I'm kind of referring to this as moles. But how concentrated does this need to be, okay, to cause this to precipitate? How concentrated do the Ag plus ions need to be to cause precipitate? So it's important to write out a expression. An ice table is not necessary, but the expression makes us get the exponents right. So Ag 1 plus PO4 3 minus. Okay, and this is going to be 3 of those and 1 of those. So in my expression then, Ag is going to be cubed, and then the phosphate ions are going to be to the first power. Now this is asking, we want the initial amount. So instead of K, we're going to call it Q, and then we're going to put a little 0 in the subscript area to indicate that we're solving for the initial amount. What's the initial amount of Ag? What's the initial amount of Ag that causes this to precipitate, given that we already have this much phosphate in there? Okay, so Ag cubed is going to be equal to, and we're going to set this equal to K as P, and we'll say whatever we solve for, whatever we get in our answer, we're going to say any number greater than this will cause precipitation. Okay, so that's why we're going to use the K as P value in place of Q. So this is going to be so 1.8 times 10 to the negative 18th divided by what the phosphate was. So the phosphate was given by this number. So that's our phosphate. So we're going to plug that in here. Okay, and then I'm going to divide by that number. So I'm going to move that term over. Okay, over here. So this will be 1.0 times 10 to the negative 5th. Okay, now take both sides to the 1/3 power, and then I get the minimum concentration of Ag required to make a precipitate. So in my answer I get 5.6 times 10 to the negative 5th molar. So, and I'm going to say, so any number greater than that, than 5.6 times 10 to the negative 5th molar Ag plus will cause precipitation. Okay, so now for the practice questions. Okay, so I have in this one, these two are very similar to the first one I just did. Okay, so you have like beakers, and with this stuff swimming around, so you got some Mg and you have OH. Okay, and they're swimming around there. Okay, and then here, a solution contains this much ions of silver and this much ions of cyanide ions. Okay, will AgCN precipitate? So this is very similar to the first one I just did. Okay, and then this one is, we want to know it says at what pH will 99% of Mg, so 99% of this number. So at equilibrium, you're going to have 1% of this number. Okay, just to give you a little hint. At equilibrium, what will be left over is 1% of this number. Okay, so what pH will it have to be to precipitate 99% of this? Okay, so see what you guys can come up with for those two, or those three, sorry.